Welcome to Methods in Biostatistics. Today, we are diving into the foundational world of biostatistics. As zoology students, you will constantly encounter complex, unpredictable biological data. How do we make sense of it? How do we know if a new treatment works or if a behavioral pattern is real? This topic matters because it gives you the essential language and mathematical tools to translate messy biological observations into clear, objective truths. Let us begin our journey into understanding how we can look past random chance and discover how the biological world truly works. Now that we know what our goal is, let us start with an intuitive scenario. Imagine you are a medical researcher. You have just discovered a new berry in the Amazon rainforest, and you strongly believe it lowers blood pressure. To prove your theory, you face a massive practical problem. You cannot possibly feed this berry to every single human being on Earth. That is simply impossible. Instead, you do the next best thing. You gather a small group of 50 volunteers, give them the berry, and carefully record their blood pressure before and after. This is the fundamental starting point of all biological research, working with a limited sample. This scenario brings us to a critical dilemma. You see changes in your volunteer's blood pressure, but how do you know if those changes are actually caused by the berry? What if their blood pressure dropped purely by random chance, or because they were more relaxed? This exact dilemma is why the field of biostatistics was created. We need a way to separate true biological effects from random noise. Biostatistics provides us with the logical and mathematical tools to make confident, life-saving decisions, even when we only have limited information from a small group of people. Having understood the intuition, let us look at the formal definition. Formally, biostatistics is defined as the application of statistical methods and mathematical principles to biological, medical, and public health data. It is not just about crunching numbers. It is the rigorous science of learning from biological data. In zoology and medicine, data is inherently noisy and variable. No two animals or patients are exactly alike. Biostatistics gives us the framework to carefully measure and control for that uncertainty, ensuring that our scientific conclusions are robust and reliable. So, how does this formal definition translate into actual practice? The biostatistical process involves 4 main steps. First, it requires the systematic collection of biological data. Second, we must summarize that data so it is easy to understand, often reducing thousands of data points into a few key numbers. Third, we analyze it to find hidden patterns that are not visible to the naked eye. Finally, we interpret the results to answer a specific scientific question. Whenever you hear about a clinical trial or an epidemiological study, you are looking at these exact 4 steps of biostatistics in action. Understanding this process helps us appreciate its historical importance. Before biostatistics became a standard practice, the medical and biological fields looked very different. Historically, medical treatments were often based purely on a doctor's personal intuition or anecdotal evidence. A doctor might try a treatment on 3 patients, see it work once, and declare it a cure. Because there was no objective way to measure success or account for random chance, this frequently led to disastrous results. Biostatistics revolutionized science by replacing subjective guesswork with solid, undeniable evidence. This historical shift brings us to the immense importance of biostatistics in the modern world. Today, its role simply cannot be overstated. Without this crucial science, we would have no objective way to determine if a new vaccine is safe or if a specific chemical in our environment causes cancer. It even helps us establish basic facts, like the normal range for human body temperature. In fact, modern regulatory agencies require strict biostatistical proof before any new drug is allowed to be sold to the public. By using these mathematical methods, we actively protect human lives. Now that we see its real-world impact, let us look at how we actually begin working with data. At the very heart of biostatistics is the need to summarize a large group of biological measurements into a single, understandable number. When you have hundreds of measurements, you cannot look at them all at once. The most fundamental way we solve this is by calculating the central tendency of our data. This gives us a representative baseline. Calculating this central value is usually the very first step a biostatistician takes when looking at any new set of biological data. This need for a single summary number leads us to our first mathematical representation, the sample mean. Conceptually, this formula takes all our individual observations and distributes their total value evenly across the group. Let us break down the symbols. The symbol x bar represents the sample mean itself. The Greek letter sigma is a command telling us to add things up. The variable x sub I represents each individual biological measurement, like a single patient's blood pressure. Finally, n is the total sample size. If the sample size n increases, our calculated mean becomes a much more reliable estimate of the true biological reality because we are basing our conclusion on a larger amount of evidence. Before we move on, let us see this formula in action with a concrete example. Suppose you are working in a cardiology clinic and need to find the baseline resting heart rate for a small group of patients. You are given 5 heart rate measurements. First, we identify our sample size, n, which is 5. Next, we apply the summation part of our formula by adding together every single heart rate measurement, 72, 76, 70, 82, and 75. This gives us a total sum of 375. Finally, we divide this total sum by our sample size of 5. This yields a final answer of 75. Physically, this tells the doctor that the central tendency of these patients' heart rates is 75 beats per minute, a normal, healthy baseline. Now that we have used this formula in a medical context, let us apply it to an agricultural study. Imagine you are testing a new organic fertilizer on wheat plants. You measure the heights of 6 plants after 2 weeks. Our given sample size, n, is 6. We need to find the average height to compare against unfertilized plants. We sum the individual heights, 14, 18, 15, 19, 16, and 14, which gives a total combined height of 96 centimeters. We then divide this aggregate number by our 6 plants. This division smooths out the natural biological variation between the individual plants. The final answer is 16 centimeters. The biologist can now use this single summary statistic to scientifically determine if the fertilizer promotes better growth. Having calculated the sample mean twice, let us visualize exactly what this process represents in the grand scheme of research. On the screen, you see a large blue circle on the left. This represents the entire biological population. For example, every single wheat plant of a certain species. We cannot measure all of them. The arrow shows our sampling process, where we extract a small, manageable group, shown as the green circle on the right. We take our raw measurements from this small group, represented by the numbers in the box. Finally, we calculate the sample mean, reducing all that raw data into one powerful representative number at the bottom. This diagram perfectly captures the essence of biostatistics, learning about the massive population by carefully analyzing a small sample. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that biostatistics is the essential language that translates messy, unpredictable biological data into clear, objective truths. Second, this rigorous framework is what allows us to safely test new life-saving drugs, track viral outbreaks, and improve crop yields. Third, mathematical tools like the sample mean are your starting point for summarizing large amounts of information to find central tendencies. You now understand the foundation of this field. Biostatistics is the ultimate tool that empowers you as future scientists to look past random chance and discover how the biological world truly works.